So rather than talking about continuity or discontinuities at particular points, we want to expand upon that to the definition of a continuity on an interval. So we can have continuity on an open interval. An open interval has parentheses, and that means that the function is continuous at each point within the interval. A function that's continuous over all real numbers is everywhere continuous. So it's important to know that that's internal, right? It's inside the interval. A function is continuous on a closed interval, and this is a typo. It should be a bracket there because closed intervals are brackets, right? So that would mean that you have dots on the ends of your graphs like this. If it is continuous at each point in the interval as well as the endpoints. Now, to be continuous on the endpoints means that you have to be able to approach either end, and the limit as x goes to b, for example, from the negative side is equal to f of b. So let me just highlight this one right here. So what I'm saying is, as I'm approaching b from the left, right here, I'm heading to f of b, right? So that the limit is equal to the function value. So this function value right here is f of b. That's what they're saying. So the limit is equal to the function value. Over on the other side, right, to be continuous on the left, right here, which seems weird because it's on the left continuous, but you're coming in, right? So right continuous, left continuous is standard phrases. So continuous from the right, continuous from the left. So I want to be continuous from the right. So I want to be able to come in right here from the right and head in right here and head to that point. So I want to be right continuous, which is this one, right? So it's a little weird. So continuous from the right. And then to be left continuous means you're continuous from the left, right? So I can come into that function value from the left, right? And then this means that this value right here is f of a, right? So even though this is on the left side, this is right continuous, right? Correct? Right continuous. And this over here is left continuous because it's continuous from the left. So don't confuse the graph, right, the fact that this is on the left with the continuity, right? It's continuous from the right because you can approach it from the right. All right, so let's discuss the continuity on the closed interval of this particular function, and they are intervals from -2 to 2. Now, with any luck, if your pre-calc teachers taught this to you well, then little warning bells should be going off in your head because you should have a sense of what that looks like. If you recall from algebra class, x squared plus y squared is equal to r squared is a circle. So when we solve that for y, and we just use the positive part, what we're looking at is the top part of the circle. So we're looking at the semicircle. I'll just make a little note. So this is the semicircle above the x-axis with radius 2. Now, in case you don't believe me, oh, I'm sorry, my number 2 got weird there. So my radius is 2. I'm trying to write at an angle. There we go. I've actually graphed it in Desmos as well, just so you can see it. So there it is. So square root of 4 minus x squared is a semicircle, radius 2. All right, so I'm going to put a little 2 to -2 right in here. I realize it's not perfectly to scale, but you get the general idea. There. That's a little better. Okay, so I want to discuss the continuity. Well, there's two aspects of it. I have continuity over on the left side, but I'm approaching it from the right. So over here on this side, I am approaching that endpoint right there at 2. I'm approaching it from the right. So over here. So the question is it right continuous? Is the limit as x approaches -2 from the positive side, from the right, for this function, is that equal to g of -2? Okay, well, the limit as I'm approaching from the right is equal to the square root of, oh, sorry, that's over here. It's equal to square root of 4 minus -2 squared, which we all can tell is the square root of 4 minus 4, which is the square root of 0, which is 0. So that's the left, or excuse me, the right-hand side of that equation. The left-hand side, we can tell, is equal to the same thing, because as we approach in, you can see it graphically, you're heading to 0. So indeed, the limit is equal to the function value, right? Where you're going to is that dot, and that dot is the function value. So indeed, this is right continuous. Now over on the other side of this semicircle, oops, I just wrote g of x is right continuous at x equals -2. So over on this other side, right here, as I approach towards 2, indeed, the limit as I approach towards 2 from the left, the limit as x goes to 2 from the left of that function is equal to g of 2, because it's equal to the square root of 4 minus 2 squared, which is the square root of 4 minus 4, which is yet again 0. And I can tell that that's the limit because the function's approaching into that value, and that value is g of 2. In other words, I'm sort of direct substituting. I'm actually kind of finding both sides at the same time because they are one and the same. I can tell it when I look at the graph. So g of x, all right, so this implies g of x is left continuous at x equals 2. And since g of x is right continuous at x equals -2 and left continuous at x equals 2, these two qualities together mean that the function is continuous on the closed interval, right? Because we have endpoints, right? We're looking at a closed interval from -2 to 2, so we're continuous on the interval from -2 to 2. The left continuous part gets us this part over here, and the right continuous part gets us this part over here. But either way, we can tell a semicircle is continuous on that entire closed interval. Matter of fact, that's a way to visualize what being continuous on a closed interval means. What it means is that you're continuous in the middle part, which we are, right? We're continuous in the interior, no problem. But the endpoints are exactly where the function is leading to. There's no jump there. There's no open circle and then a dot somewhere else. There's no asymptote. That's what we're saying. So we actually have a closed interval, and the function limits at each of those ends is going exactly to where the function values are.